GE Transportation, Wabtec, and Fably. And so we make equipment, we make manufacture locomotives, a lot of the components that go both in freight and transit locomotives, as well as a lot of the digital electronics and software. And so Dharma and I come to you from the software segment of the business, and we oversee product lines that manage and optimize the movement of things across networks. And we have sister product lines that look at things like shippers and connectivity of that data, as well as yards and optimizing movement of things within yards. So with that, just real quick highlight, maybe we can move on, Dharma.
Hold on. Okay, just wanted to give a quick primer on some terminology that we will be using today for those who may be new to the industry. For those who are already familiar with it, it may be repetition, but I will be very short. First of all, block is a train block. Block is basically a group of railroad cars going to the same intermediate destination. And then a block typically has an origin location and a destination location. Block to train assignment is basically which train would carry the block. And block to train assignment will also have a train will pick up this block at this location and train will set it off at this location. That's called block to train assignment. And train schedule is an itinerary or timetable of train departure and arrival times from train's origin to destination, including all the intermediate activity locations. And also would specify crew change locations as well. Operating plan is a block to train assignment plan and train schedules for the entire rail network. Designed basically to move all the shipments from origin to destination. And meet pass plan is a detailed plan of train movements on track segments, specifying specifically which train will be taking which track. In case of single track with siding, it would say which train will take the siding and which train will take the main track while the train is moving towards this destination. And traffic mix or mixed traffic is basically means composition of freight and passenger trains. Normally on the freight railway, you will have various type of trains operating. You may have a merchandise train, intermodal train, multi-level train, coal train, grain train, and also passenger train. So that's what we mean by traffic mix.
Cool. Yeah. So to kind of set the stage for how we're approaching this, if you've been following the railroad industry for a while, and I know there's a lot of students on this call here, so I'll quickly kind of recap what's been going on.
Can you speak up a little bit, possible?
Yeah. Is this any better?
Yeah.
You can better now? Yeah. Sorry about that. We're kind of coming towards the right-hand side of the bell curve on the PSR spectrum, right? So PSR has been going on for several years. Precision scheduled railroading started off with CN, CP, and kind of worked its way throughout the network and throughout the large class ones. And essentially, it was a different philosophy for how to manage and operate a railroad. And it has been very successful in generating a lot of profits and in generating much more efficiency for the day-to-day operation of a railroad. You're seeing dwells get a lot better. You're seeing operating ratios get a lot better. Velocities get a lot better. You're seeing fewer trains that are longer. So it's provided a lot of benefits overall. But now that we're getting to the other side of that, what's next? How does a railroad optimize itself to be more competitive and to grow its business? So the answer for that really lies in the network. There's a compelling opportunity to be realized by rethinking how to operate the network for optimum performance and then to drive growth. and then eventually to take PSR to the next level. So we start off with that as kind of our launching point to say, okay, we're coming to the end of the PSR spectrum. What can we do to make, what can we as a railroad, in this case, not as Wabtec, do to make our business more profitable and to grow? So with that, let me move on to the next slide. Why do we talk about the network? Well, it's kind of an obvious thing, but it's worth digging into in some level of depth, right? So the network is a lot of different things. It's not just the rail, it's the locomotives, it's the empties, it's the workers and the crews who have to communicate back and forth. It's the operating plan that connects all these together. It's important to be able to tie these different parts of a network to an overall operating plan so that you can see the benefits, which are on the right-hand side of the screen, so you can improve the network fluidity. It's hard to improve the fluidity of a network if you don't take into account all the different actors on that network, and I'll use that term actor fairly generally in this case. It's hard to improve on-time performance and to make it reliable if you don't take into account yard clocks and terminal dwell. So we need to look at the network as a whole, not as individual stovepipes, as any good optimization problem to be starting off with. So it's with that kind of mentality that we build a playbook. So if we go to the next slide. So we've kind of outlined a high-level next generation playbook. So it starts off with service designing. So designing of the overall operating plan for a network. What's the right way to do it? What are some ways in which it can be made more resilient? From that, we move on to real-time visibility. So that takes into account the ability and the benefit of having various data streams come into the same place to have visibility not just between data and humans, but also between different parts of the organization that use that data. Real-time optimization. So this is different from service design, which may have a longer time horizon. Exceptions always occur on a day-to-day, minute-to-minute cycle. And so it's very important to be able to resolve the conflicts and reset your plan so it's trying to adhere to that operating plan that came out of service design, right? And then you have to take that plan and you have to actually execute it. And the dispatchers are at the front line of that. And we have to make it so that the dispatcher can be doing more than mundane management of various entities, but is doing higher level cognitive work. And we'll talk to kind of what the load is on a dispatcher today and what it ought to be in the future. And finally, that should wrap around to prediction. A lot of very, very good data is being generated and collected. And a lot of course corrections are made throughout, that middle stage of real-time optimization. So it's important to take that to predict what will happen in the network, in 12 hours or maybe even further down, maybe on a different part of the network. It's the typical butterfly analogy that we always talk about. And then to wrap that back into real-time optimization and also into service designing so that the next iteration of a plan can be made more resilient. So our overall philosophy and playbook looks sort of like this, and people can enter it at various parts of wherever their network is currently, wherever their operations are, where the pain points are. So we can talk more about that too.
So again, from prediction, we would be able to identify actionable items or actionable insights, and that will allow us to not only do the near-term resource planning, but it will also help us do a better real-time optimization. With that, so let's walk through each of these steps in more detail.
Thank you, Dharma. Okay, so service designing. Let's take a look at how it's kind of generally done. I mean, it varies a lot, where you are and how large and complex the network is, but largely the overall operating plan is a very, very complex multivariate problem to solve. largely it's addressed to using spreadsheets. It's largely addressed using a lot of communal knowledge that's been generated through the team that owns it and builds it, right? So how long does it really take for our train to get, from point A to point B on Monday, Wednesday, and Friday? Yeah, that sort of knowledge can now, in the future, that should be simulated using real physics models. What's the right way to develop a blocking plan? These sorts of things are done largely manually, but they're also done heuristically, and there's a lot of room for optimization here. Some of the other challenges currently that we hear people facing is it's a large and complicated problem, so it's not one that's addressed on a rolling basis. You might add or change plans several times a year at best, but as we've seen in the last 6 months and maybe 2 years, demand conditions change very rapidly, and it's very important to be able to adapt to those much more quickly. And so it's important to be able to say, hey, what if I change my schedule from Monday, Wednesday, Friday to something else? It's important to know what the impact is on, on a trade war or on a pandemic or on a hurricane that's going through. So you should be able to adapt quickly. You should be able to take more things into account when you develop a service plan, and you should be able to do so in a more rapid fashion that's more deterministic. So if you go to the next slide, that's kind of what we predict as our next step in the evolution of the railroad. So precise forecasts based on history, on economic indicators, closed loop of being able to load empties and loaded trains, and creating a balanced plan, taking into account the blocking and all the various elements of this. So I'm not going to steal Dharma's thunder. Dharma, you've got a really good slide coming up next. It talks about how these all tie together.
Okay, so basically, again, service design is a complex space within the rail industry. What you see in this slide are different elements of service design process. Each box requires some modeling, like optimization and or analytics. The future of service design is to have all these aspects integrated, or may even be solving blocking and train planning problem all together at once rather than dividing into the different pieces. I will not walk through each step, but key highlight is, again, block optimization is necessary to create an optimal set of blocks for each yard terminal over the entire rail network in order to move the traffic in a most efficient manner. Once blocking plan is developed, then train plan is created using the blocking plan as an input. This will include train route selection, block to train assignments, and meet-pass feasible train timetable or schedule generations. The optimized train schedule for the whole network would then be input to the resource planning. That includes locomotive and car fleet sizing, crew requirement forecasting, and track and terminal resource planning. Eventually, all those estimated resource requirements are translated into a railroad's financial planning.
And just to underscore a point Dharma was making, you saw a lot of those individual blocks, right, of a blocking plan or a crew plan. The vision is to have a lot of those connected to one another, so they're feeding back to one another. The real future lies in those arrows that connect them together, not necessarily in the individual optimization problems themselves. And that's where we see a lot of the value coming in, and where we see ourselves going in the future too. Sorry, yep. You can keep going. So step 2 in that spectrum is real-time visibility. What does this mean? So right now, challenges are that there's a lot of data. Great, it's being created, but it's not really being made consumable. It's not really being made consumable both to all the humans who need it, but also to all the different systems that need it. So it's important to have a a visibility strategy to make sure that the data lakes which are being created and being used are properly structured. And so that the level of reactive communication that's occurring across the network is reduced. And so we see that getting better with tools that allow that to occur. So, you know, if you go to the next slide real quick. Thank you. So blocking and tackling, it's important to have train graphs that show you where your trains are, where your crews are, what's expiring, what's not. It's important to know for the dispatcher and for other you know, maintenance of way workers, what's coming their way, what's, you know, going to enter their territory, what's late, what's not. It's also important to be able to share that data across different optimization problems in the real network. Because that creates better decision making. And it also sometimes creates harder problems to solve, but we're to the point now where we can start to really solve those global problems and not be stuck in stovepipe optimization. It's important to do this so that you can start to share exceptions with other stakeholders that might need to deal with them. And so frequent ingestion of latest state is key. And then visibility across the network, both up to finance, to sales is important, as well as to the folks who make everything work on a day-to-day basis. So here's a quick example in the next slide of what could happen and what actually does happen on a fairly regular basis, right? So here you see a shipment that's coming out of the left-hand side. It's going across dispatcher one's desk and then dispatcher two's desk and, you know, maybe a yard in between, and then eventually to a receiver across a few more dispatchers. But this dispatcher, he or she has a lot of work that they're doing, and their goal in life is to move that train out of their territory as fast as they can. It's hard for them to know what's going on in dispatcher 3 as a result of you know, the impact dispatcher 1 might have by shoving that train out. It may be that there's congestion created further down 12 hours later. It may be that a yard somewhere else can't accept a higher priority train. It may be that something else is delayed. So it's very important to be able to connect these dots and then to know, you know, what the impact of one butterfly wing is on another. Because really at the end of it, what you're talking about is the intelligent distribution of delay slack across a network. And that delay slack can be, you know, train delay, human delay, whatever, what have you. But managing that delay slack is key to getting the network back to its original plan as quickly as possible, while still maintaining the key KPIs and metrics that are important for the end customer, in this case, the receiver, but also for the finance folks who make the world spin. So it's these sorts of real-time problems that we need to be able to solve by first having that first stage, which is a good plan that you can execute. You can actually execute through all the meets and passes. 2, having visibility across all the different actors to one another. And then 3, being able to actually optimize it when there's exceptions. So if you go to the next slide, what we see is a future state, which in some cases is a current state for some of the solutions that we're working on, in being able to deal in very quick increments, you know, 2-minute increments to changes that occur on the network. So if there's, if a train is launching later, if there's a power failure and a train just lost a good bit of horsepower, you know, we need to be able to adapt to that and change plans and change routing. So for instance, there may be 2 ways to get from point A to point B on a railroad's network. It's important to be able to automatically assess both those paths and see what the pros and cons are of both those paths, and say, hey, you know, maybe I had to give the dispatcher the option to route the train through the second path, but it may have the impact of a crew outage. What's better, right? So real-time optimization is an important stage in being able to build plans in real time that adapt to the changes in the network, both to improve the performance, but also to make sure that the network and all of its actors are adhering to the overall plan that was generated in the service design step. So Dharma, I think you have a great slide 14 here that kind of talks to some of that at a more technical level.
Okay. Again, what you see is the Wabtec's integrated movement planner system. It is fully integrated with the railroad's train control system, including dispatch systems. Dynamic updates from the train control system is continuously provided to the movement planner. So when it generates a new plan for next 12 hours, every 2 minutes, latest events, including train location and track block, and all that information are incorporated when you generate the next plan. The latest generated train movement plan is then is published and automatically sent to what we call the auto router. And what auto router does is basically looks at the signals availability, whether it's clear or not, and then sends a request to the dispatch system to clear the signal for the trains to move. So basically the key is that generating a plan and executing a plan is all done automatically. So dispatcher is involved only to handle exceptions. Okay. With that, I'm going to just show a quick video of the movement planning system. So this, let me pause a little bit. What you are seeing is just a demo, sort of like animation of the movement plan. How it operates. Again, dispatcher may not necessarily see this screen, but it's just to demonstrate to everybody how it works. On the top, what you see here is, hold on. These are like a track topology, and you see trains moving different directions, some going to the left, some going to the right. And then the bottom is basically, obviously horizontal axis is space, and the vertical axis is time. The current time is over here on the top of this little red horizontal line. You will see it moving as I play the animation. It will keep moving, going down. Then as it moves down, it basically shows how the train is moving on the track. So this is sort of like a time-space diagram. So let me just run this. So these are different trains taking siding, going to the main track. And then you see that line is moving down. So you can see where it is. So you can just simulate how the trains would run. That line is over here. See, it's moving down. Okay, so I think you got the sense. So I will just pause it here and get back to the presentation. Ken?
Yeah, thank you. I was just grabbing a quick glass of water here. So we've talked about building the right plan, connecting all the players so that they have knowledge of each other's activities. We've talked about optimizing outside of stovepipes and connecting stovepipes together. And then we've talked about optimizing on the day of operations to exceptions, and exceptions that arise from, good decisions that are being made by actors on the network, or things that are occurring outside, like actual delays or storms or whatnot. At the nexus of all these is the dispatchers, and the role of a dispatcher has evolved pretty significantly over the past several years, largely because of automation and because of the data that's being thrown at him or her. So whereas previously, maybe 5-7 years ago, a dispatcher was doing a lot of manual work trying to figure out what how to shove trains out of their network. Her territory, his territory, has grown because of the amount of automation that's been afforded to them. And that's a journey, and that journey is not over yet. There's still a lot of work that a dispatcher does that maybe should be done by a machine, so that the dispatcher can focus on improving overall metrics and improving overall performance and fluidity. Dispatchers have other problems that they're dealing with, right? So there's lack of visibility for the impact their decisions may have in other places, but there's also there's also changes, differences between region to region. So one region may need to be managed in a certain way. There's variation between how two dispatchers would handle a problem. And so it's sometimes difficult to understand from a network perspective or a business perspective how a network will perform when John may act differently for a delayed train entering a yard than Mary would 2 days later on her shift. So we need to find ways to make these decisions more consistent. And important to that is having the right data and the right simulation tools and the right day of operations, exception handling tools ready. And then also being able to allow the dispatcher to execute their actions and their communication to the engineers or whoever. Maybe they're talking about authorizing a repair job on a certain line of road. That's a lot of back and forth. Automating a lot of that back and forth makes it seamless, makes fewer mistakes occur, but also makes it consistent from how two different dispatchers would do it. So if you go to the next slide, our future vision of a dispatcher and of the dispatch activity has auto routing.
Can you speak up again? I think you were.
I'm sorry, I was leaning back here. Is this any better?
Yep.
All right, thank you, Dharma. So our future vision of a dispatcher is rooted in auto routing, which is a large part of the automation story. It's also rooted in consistency. We're looking at things like moving block, which would reduce the headway between two trains, and it's a cognitively difficult thing for a dispatcher to deal with. So this is a large part of the automation that has to be done with good data going in and with good plans being generated. The dispatcher is currently monitoring a lot of subsystems. Part of our vision is to automate a lot of that proactively and to give the dispatcher very simple binary decisions to make so that he or she can make those decisions and move on. And part and parcel of that is having a clean UI and having a lot of data that's presented in a way that today's generation can handle. Today's dispatcher may have grown up in a different environment where they're used to seeing a lot of fast moving action, maybe in a video game or whatnot, right? So being able to speak to them at that level is important. And so the next generation of dispatch solutions are going to have a lot of these benefits baked into them. And so when the dispatcher is given this information and when the dispatcher is given an exception handling plan, it should have taken into account whatever has occurred. It should have taken into account the optimum plan that was built. It'll have taken into account what's going on in the line of road and the impact to a crew outage. And then the dispatcher doesn't have to juggle all these different things in his or her mind to come up with the right decision to make. So I'll stop here. Dharma, is there something you want to add to this slide before I move on?
Yeah, I guess just to reiterate that the next gen dispatchers who would be just handling exceptions, and they would be doing more value added items to see how to move trains quickly and then try to minimize any kind of unexpected events. But as far as running the train, then the system will automatically generate plan and take care of clearing the signal through auto router and move on. So that's the vision for the future dispatch. And also, currently the dispatchers only have their dispatch network view. As you can see here, they would have a more like map type of dispatcher view, so they can see where other trains are, maybe even in other territory, which train is about to enter their territory. So they would be able to see that a lot more easily. Okay, Ken?
Yep. And so the final step, but also in a very real way, an intermediate step in the evolution is proper prediction. So currently we see a lot of data being generated. Again, I've said this several times, but not a lot of predictive insights and very little actionable decision-making that's done as a result of that data. The primary focus of all the brains that are involved in this, in managing this large network, is responding all the time, as opposed to predicting and preempting, right? And so what we see as the next step, and honestly to copy a lot of the best practices from aircraft engines and from a lot of the other large complicated networks like power networks, is predictive actions that are automated so that exceptions don't occur, or so that the humans in the loop are really just adding judgment calls. And to bring that level of sophistication is part of the vision for the next step. So if you move to the next slide real quick, so here it's a little bit hard to see, but a very important thing would be to be able to know when, for instance, in this case, congestion may occur. So I'm just going to make up a fictitious example. Say a train is launched from Melbourne, Florida, where I'm at right now, right? It's very hard to know that if it's launched at a certain time versus maybe 2 hours earlier or 2 hours later, it might cause backup or congestion entering the Allentown region, a few hundred miles away, a day and a half later for another train. It's important to be able to connect that dot and say, hey, maybe you ought to launch it a little bit earlier, or maybe you ought to break that train up into 2 different trains as part of a closed loop, feedback to the overall plan that's being generated. It's this sort of predictive action that's the future of where all this is going. It's rolling that back into a what-if analysis to say, hey, if I would have planned that train differently to begin with, could it have been more resilient to a hurricane coming up, or could it have been more resilient to a delay from a shipper? It's closing that loop and having that visibility to the flexibility in the plan that gives true insight into how a network ought to work. It's not necessarily important just to have the right data. It's more important to ask the right questions and be able to predict what will happen to a short and a medium term. Allows all the smart people who run the railroad to ask different questions and then to solve problems in a different way. And I think that's what we're trying to drive this toward from a vision standpoint, and very real from a product standpoint as well. So if we go to the next slide, we'll just try to wrap all this up.
Maybe I'll just add a few points just to reiterate what Ken is saying. The prediction capability will allow one to simulate how the railroad would look like for the next few hours or few days, and identify potential problem or issue areas and take necessary action to mitigate the problem or the issue. The action may be rerouting certain trains around congested line or terminal, or a taxi crews to away location to ensure enough crew is available to run the trains on time. Or it may be like what Ken was saying, maybe holding off on launching the train at the origin so that 2 days down the road, then it doesn't get into a very congested line or terminal. Some trains do have option to change the origination time. Some trains run on a schedule, but some trains you have a flexibility to even change the origination time, also to even reroute those trains. these alternative mitigation action could be re-simulated using what-if capability and identify the best action to mitigate the issue with minimal adverse network impact. Okay.
Yeah, good point, Dharma. So to kind of bring us all back to the top, we talked about kind of this whole playbook we have of moving to the next generation past PSR, and in effect to allow railroads to, look, we all care about the bottom line, to grow the real market share of goods that are transported across a continent, right? And so building the right plan to begin with that's realizable, that takes into account all the different actors, is step one. And moving beyond that to allow all that data to come together, both to the machines and the humans that use it to make good decisions, to be able to cognitively understand what's going on, that's step two. And then dealing with all the real world exceptions that occur in a way that still adheres to the overall service plan or the operating plan that was designed. That's step three, but that's a very hard step to do, because that's taking into a lot of data and a lot of exceptions into account. And step four is giving actionable insights to the people on the ground who are executing their day-to-day job. The dispatchers and the crews, we didn't specifically talk about them, but they're part of that fourth block. To give them the power to make the right decisions on a quick split-second basis, and to make that consistent across days, across different humans who make those decisions. And then finally to take all that data and all that course correction and to roll that into a prediction engine that allows the enterprise to, one, know what will behave, or what will be occurring over the next 12, 24 hours or even further, but then also to roll that back and to make better plans which are more resilient, so that eventually the whole goal is to give the end customer better ETAs, better reliable service, ideally cheaper service, so we can compete with all the other modes of transportation out there, and at the end of the day to grow rail market share, which is what our customers care about the most. So that's kind of our overall vision. We'd love to talk more about this with you offline. A railroad can enter this really at any of the first four stages, depending on where they are in terms of maturity and in terms of how connected and how available some of the data is. So we can cater a good approach depending on just kind of where you are. I mean, it might be a small railroad, it might be a large railroad, it might be a railroad that just has coal, right? Or it might be a railroad that has a very complicated mixed set of goods that are being transported across the network with all sorts of different priorities. So the solution is going to vary, but the fundamental building blocks to getting to the next stage, to winning market share, really are going to stay largely the same as you see them here. Dharma?
Yep, I think that's good. I don't have anything to add. I think you said it all.
Well, thank you very much for this very, very interesting presentation. Really cool stuff, lots of information, but I think you are headed to the right direction. So thank you so much for sharing this with all of us. So I have some questions here in the chat room, but if if anyone wants to ask a question, you can. I have allowed you guys to unmute yourself. So if not, I can just go ahead and start reading the ones that I already have here. So is there anyone that has any question for Ken or Dharma?
Sounds like Hemant had a question here. He was asking, what is the forecasting horizon and granularity?
Yeah. If you want to go ahead with that one, I was trying to give people the opportunity to speak.
However you want to do it.
Those who are in the chat.
Hemant, did you, did, I'm not sure if you wanted to speak to your question before I and Dharma address it.
That's fine. Like my question was around what's the forecasting horizon, the step one, like how long do you forecast and what granular level is a day, hour, or maybe a week? That was sort of I wanted to ask, understand. Yeah, guys.
So for the real-time optimization, our planning horizon is generally 8 to 12 hours, but for prediction, the planning horizon may be few days, 12 hours to a few days, 72 hours, 96 hours. So it depends on which system you're talking about.
Yeah, largely,
It could be even 10 days.
exactly. And to kind of draw a line under Dharma's point, it varies based on what the need is for the customer and for the network, right? Some networks might be stable enough that it's valuable to have a plan that goes out several weeks. Some networks, you might know that you're going to get a lot of variability in 72 hours, so it doesn't make a ton of sense to have a garbage in, garbage out plan that's, you know, a few weeks long when you know full well that you're going to get a whole load of unplanned trains coming in, you know, 4 days. And so the short answer to your question, Hemant, is it's configurable and it's customizable to what makes sense for the railroad to plan out so that you're actually getting actionable use out of that.
Thanks, guys. A nice presentation, though. Thank you very much.
Thank you. So I have one question here. How predictions are driven into the plans and how they are used or they are consumed in real-time operations?
Ken, would you like me to?
Yeah, sure. I'm not sure I fully understand the question, but maybe you get it better than me, Dharma.
I think the question is how prediction is brought into the plan and real-time optimization. The thinking is that we would do the prediction for next few days or 10 days, depending on how stable the railroad's train network is, and then be able to simulate forward. And then be able to see where the problem may arise, where the congestion may be arising on certain lines or certain terminals, or it could be that you may have to, if it's congested, then you may have to reroute the train, or you may have to hold off on launching some of the train from the origin. So that information will go back to the input that goes into the real-time optimization. And then you do what-if analysis and with different alternatives, and then whichever alternative gives you the best result with a minimal adverse impact to the network, then you would say, this is the plan I want to follow. And then let the real-time optimization start executing that plan. And you could be doing that multiple times in a day.
Fernando, let me try to give you a very crisp example. Say, for instance, a train's leaving from Melbourne and going to Seattle, right? Long, several-day trip. And something occurs in between in real time that causes now new information that the crew is going to time out. Well, that's a prediction that, hey, your crew is going to time out 2 hours before you're expecting it to time out. How that's driven back into operations is it gives the dispatcher and all the other folks who care the option now to swap the crew or to work an exception so the crew can stay longer, or to do whatever is within FRA rules to allow that to be handled. And, and that exception and those options are given to the decision makers who are humans and as choices to be made. That's a clear prediction, and that's not even so much of a future thing. That's a very real part of many of our solutions now. That's really not again. Hope that answers.
The same logic. If yard is going to be exceeding a capacity, you will be able to see that this yard is going to be flooded with trains. So you can take different action to avoid going through that terminal, certain trains, by either holding off on it or maybe rerouting. Very similar to what we were saying before.
Okay, great. Thank you very much.
Okay, so I have one question here about PTC. So how the PTC system will be used for future train operation? Will it still be used as overlay or main system? How will they interact?
Did you say PTC or
Yes.
particle train control? Okay. Ken, would you like me to answer first?
Sure, you
Or-
can. That's not a system we directly influence. So I just want to be careful that we don't speak for the owners of the PCC enterprise, right?
However, the PTC is going to provide more accurate information on where the trains are, what the train consists are. So we could utilize that information, and also it definitely will help on coming up with a moving block system, because you have all the information that's needed, and it can tell you how many feet or how many miles apart trains are. So that's going to really enable us to do a lot more, especially on the prediction side, and also on improving the dispatch efficiency.
Okay. And when do you guys think we will achieve the future state? That will be within 5 years, 5 to 10 or more?
Well, I mean, again, depends on what functionality we want to add, but certain functionality is already there. We already have that. So, again,
Yeah, so David, the answer to that really is twofold. One, it depends on how much of the future state is a good business proposition for the customer to be at. If a railroad can't invest in that level of data integration, then the future state should be pushed out, right? Because there's no ROI for them. If a railroad has a lot of complicated issues where the future state really can drive higher market share and can really drive better cost, I think it can be done even with less than 5 years. So I think it really becomes a business decision on how quickly a railroad wants to adopt that, to be honest.
Okay, just quickly, thanks Dharma and Ken for your presentation. It was very interesting, and I liked your comprehensive, interesting vision of the future. And I guess I was just really thinking, when you talk about autonomous trucks, they're always putting dates out there that we're going to have autonomous trucks within 5 years or 10 years. I know the bar keeps moving as well in terms of when we have them. So I was just wondering if there was a vision for when the railroads could achieve this. So thank you for your answer, and thank you for your presentation.
Thank you, David.
Hey, David, I'm going to just editorialize a little bit here. Back when I was in business school, there was a book that I was forced to read. It was called Only the Paranoid Survive. It was by the founder and CEO of Intel, right? And I think the message of that book is stop worrying about when something's going to happen and start dealing with it today, because eventually it's going to happen. So, the way I like to deal with these things is eventually we know there's going to be disruptions in the competitiveness of various other solutions. And so, automated trucks might be 10 years out, or Elon Musk might wake up tomorrow and have another brainstorm idea that we have to worry about. So I'd like to deal with that eventuality and start making our customers more efficient today.
So David, we're kind of already, in a way, we already have a foundation, because we are able to use the auto routing movement planner is creating the movement plan, and then auto router is executing that movement plan with the dispatch system. So we're kind of already halfway through there. So I think we'll have to just continue building on that to go to a complete automation.
Okay, thank you.
Thank you. So another question here. How do you intend to cover interchange where two different enterprises may conflict?
Well, key one is obviously we will have a better ETAs for when the trains would be arriving. The other thing is when we have railroads using the same system, like for example, the same dispatch system, then we would be able to treat those multiple railroads as one entity and be able to plan even better.
Okay.
Ken, you want to add anything?
Yeah, so totally underscore your point, Dharma. Just one other flavor that I'd add to that is, again, I see this from other industries, that there's a benefit in sharing information and sharing data. It just has to be turned into a financial benefit for all the players involved. And I think that might be the missing piece is increased visibility should be clearly shown to the various parts of that interchange as something that can drive financial metrics. And I think better ETAs are a big part of that, but there's a lot more we can do. But I think that's a partnership model and a partnership deal with various folks who own their data and may or may not be totally on board with sharing it with other folks. But I think that's an evolution. And in the ebbs and flows of the business cycle, when things get tougher, folks tend to share more data so they can all survive, right? So maybe we're at the point where we can start sharing more of that data going forward. I'm not sure if I'm answering your question there or just being obfuscating it more. Go ahead.
Okay, thank you. One more here. An optimized network could lead to lower infrastructure and other capital needs to locomotives. How do we make sure the optimized system is not over-optimized? This is have sufficient functional redundancies and resiliency to bounce back when we have a sudden spike in demand in the future.
Fantastic question. Go ahead, Dharma.
I guess my view is when we create a plan, we have to create a more robust plan so it's more resilient. If something goes wrong here and there, it is able to recover from those deviation from the plan quickly. And also being able to plan ahead and be able to see what issues you may run into down the road upfront and be able to take necessary actions, we believe is going to really reduce those number of unexpected events and train delays, and also going to reduce the resource cost or the resource waste that was not planned, but because of delays and unplanned event, you ended up using more resources. Those would be minimized. And if the situation changes, if the traffic demand goes up and down, then obviously be able to replan quickly and generate the new plan and be able to execute that will also help.
Hey, Rapik, that was a fantastic question. I just want to editorialize on that a little bit from a less than technical perspective. So a couple of threads to that. Thread number one, you want to be able to have some insight into when that sudden spike may occur. And that's where good predictive analytics starts to come in. But a lot of these spikes, I really get you're not going to be able to predict, right? Because that's just the real world. The second part is being able to design plans with enough, with a quantifiable enough capacity in them, so that the extra capital that you have budgeted in costs you less than the recovery that it would take for that spike had that capital not be put in, right? So if you look at it from a business case standpoint, if I budget in, I'm just going to make up a number, a few extra locomotives for a demand spike, what is the counter on that? Like, say I had that spike and I couldn't address that demand, what would it cost me? Maybe I have to go lease a local from neighboring railroad. Maybe I have to lose business to somebody else. What's the statistical significance of that spike occurring? Is that a Poisson distribution where you can see it happening every 4 years? Like, so I think those are the sorts of considerations that go into account when we have to figure out how much extra capacity to stick into a plan and then where. That's as much a business question as it is a technical question.
Well, thank you. Thank you so much. Great discussion. Thank you, Ken, Dharma, for your time and for sharing this knowledge. Very interesting presentation. Excellent talk. And thank you all the participants. Thank you very much for joining. And please stay tuned. We will have very, very interesting talks and webinars in the coming months. So please stay tuned to the RAS website. We will be sending out an email with the link to the presentation and the recording session. Also, you will have a copy of the slides available in the RAS website. So thank you very much for joining us and have a great, great day. Bye-bye.
Yeah. Thank you. Bye-bye.
Thanks, guys.
Thank you, guys. Have a good day.
Thank you.
Thank you all, Andrea, Dharma, and Ken. Great job.
Thank you.
Okay. Thank you. Appreciate it.
Joining us.